Hello, this video is on the kinetic molecular model, and actually the next three videos are, and I'm following Young and Freedman's University Physics. So we're in chapter 18, which is on the thermal properties of matter, and we did a video on the ideal gas equation and on the molecular properties of matter, and now we're in this third section. Called the kinetic molecular model. And I'll have chemistry videos that I'll also link eventually to this. The chemistry covers this, chemistry chapters on gases cover the same basic material, but it's a little slower. Boy, Young and Freedman hit this stuff pretty intensely when you think of how it's spaced out a little bit more in chemistry. Well, this section was so thick, it's a thick section, that I decided to break it up into three individual videos. And this is the first on collisions, that is of molecules in a chamber or a space, a volume, and gas pressure. So we're going to connect a kinetic molecular theory here. We're going to connect the collisions of molecules with pressure. Okay, let's start. So the assumptions of this section are as follows. So first of all, let's assume that there are lots of molecules in any container of volume V. So if you have a helium balloon, you've got lots of helium atoms in that balloon. And capital N is the symbol we're going to use for the number of molecules. Don't confuse it with the small n, which refers to the number of moles. See the previous video. Large N we're going to use for all the molecules in that container of volume V. Now, the size of those molecules is relatively small compared to the distance that we're talking about here in the volume, okay? So size of molecules small. The molecules we're going to assume are in constant motion. As we know now that temperature increases the motion, that's basically what temperature is. Colder it gets, the less motion there is. The hotter it gets, the more motion there is. We're going to assume that these collisions with the wall of the chamber or the balloon or whatever it is, we're going to assume that these are elastic collisions, by which I mean that no energy is lost in the there's a conservation of kinetic energy between collisions. And then the container walls, let's say, are perfectly rigid for the sake of argument. Okay, so let's go. So what are the number of collisions of molecules per time with this so-called rigid wall? Okay, so to model this, let's assume that there's an imaginary cylinder around a certain area of the wall, and let's say that the area, and in my edition of Young and Freedman, I don't know about yours, you probably have a newer edition than I do. On page 620 in mine, I have the 12th edition. So in 620, there's a diagram, of a little circle on a rigid wall with molecules, hitting that wall and bouncing off. Bounce, 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 okay? Now, what is the volume of this imaginary cylinder in which these molecules are? Well, the volume of a cylinder, you'll remember from geometry, is the base times the height. So we'll just call that base A. Now it may not be a cylinder. It is here. We're going with a cylinder, although I'm not sure if it matters that we go with a cylinder. But let's go with a cylinder, okay? Because it's for any kind of three-dimensional shape, it's going to be the area times the height. Okay. So what is this height of the cylinder with these molecules in it? Well, you know that distance equals velocity times time. And so in a infinitesimal amount of time, the velocity times the infinitesimal time is going to give us the height of this imaginary cylinder. Now, V here, by the way, in Young and Freedman is Vx, because we're just going to simplify it and think of the one-dimensional perpendicular kind of hitting. The others, I suppose you might say, cancel out, so that we just have that x dimension. But I left the x's out. So the height of this imaginary cylinder is going to be distance times time I'm sorry, distance equals velocity times time. So v dt gives me the kind of imaginary height. So a v dt is going to give me the volume of this imaginary cylinder. Now, N divided by V is the number of molecules per volume, right? N is the number of molecules, V is the volume. So the total number of molecules, say, in that cylinder is going to be total number of molecules divided by that volume, okay? So, but we've just said that that volume is going to be A V dt. Let's also say that half of the molecules are hitting it and half of it are bouncing away. So we're gonna half this number. And voila, there you have it. The number of collisions with the wall in that particular area is going to be 1/2, because some are moving toward and some are moving away. The number of molecules per volume times the area they're hitting times the absolute value of V, because we're looking for the quantity, not the direction here, dt. And there you have it. The number of collisions per time on a particular area by the molecules in that container. Okay, there you have it. That's just equation. Doesn't even give you a number for that equation. I guess this is a working equation. Okay, so let's talk about what the rate of change of momentum of all these particles is. Well, you'll remember from a long time ago in a faraway place that momentum equals mass times velocity. Okay, great. I remember that. Yeah, P equals mv. Now, the change of a momentum of an particle, so it has a momentum mv hitting the wall, and then it has another negative mv, or however you want to put the sign, going the other direction. So we have a change all the way from positive mv to negative mv. That's a total change of momentum of 2 mv, right? The change in and out. Okay, so 2 mv. So for all the particles, we take the number of collisions of the particles, which this is the number of collisions of the particles, and we take the fact that the change of momentum is 2 mv, and what we have is that the infinitesimal change of momentum is equal 1/2 n over v a v dt. That's from the previous PowerPoint. That's the number of collisions, on the wall, times the change in momentum, 2 mv, that we just got there. Now there's going to be some canceling here, right? Algebra. You're in probably second semester physics. Algebra. So the 2's are going to cancel out, and we're going to have a v squared. We don't have to use the absolute value because v squared is going to be positive anyway. And so voila. We have that the change in momentum per time, I'm going to bring the dt over here, so I have change in momentum per time. It's going to be what's left. It's going to be n over v times a times mv squared. And there you have it. And this is equation 18.9 in ye olde Young and Freedman. It is the change of momentum per time, instantaneous rate of change of momentum in relation to this being the mass, of a particle, and so forth, the number of particles, the velocity of the particles, the area that they're hitting, and the volume of the space. Okay, yay! Now, this is the last part of this video, and I haven't even covered one page of Young and Freedman. So what's the pressure in relation to these molecules we're talking about? Well, Newton's second law is F equals ma, but he also formulated, actually the way he formulated was that the force equals the change in momentum per time. Okay, so we just did a dp/dt, remember? We just did one. And so pressure is force per area, right? Force per area. And so if we take the equation from the previous, if we take this dp/dt and divide it by the area, so we basically go back here and we divide this equation by the area will cancel out, and we're just left with n mv squared over v. Is that what I have here? It is nv squared, n mv squared over v. That's the pressure, the force per unit area, and the area cancels out from the previous page, and we're left with the pressure being the total number of molecules in a particular volume times the mass of those molecules times the velocity of those molecules squared. Okay, well, that's a lot. But that is the first section of Kinetic Molecular Model of an Ideal Gas, section 18.3, and this is the first subsection of that section, collisions and gas pressure. So we'll come back in a moment, depending on when you watch it, to do kinetic energies and molecular speeds will be the next one.